Hello, students, this is Recitation 7. Our learning objectives are to calculate probabilities of a binomial random variable, calculate probabilities of a Poisson random variable, and calculate probabilities of a hypergeometric random variable. It is estimated that approximately 45% of baby boomers are still in the workforce. 6 baby boomers are selected at random. What is the probability that exactly one of the baby boomers is still in the workforce? So here, this is following a binomial distribution. And so here in bold in my handwriting is the PMF of a binomial. And so here in this example, we have the sample size, N, which is 6, because there's 6 baby boomers that are selected at random. And the number of successes is the baby boomers that are still in the workforce. The probability of success is 0.45 because it says that it's approximately that 45% of the baby boomers are still in the workforce. And so the probability of failure is 1 minus the probability of success, which would be 1 minus 0.45 or 0.55. And so part A is asking, what is the probability that exactly one of the baby boomers is still in the workforce? So that's equivalent to saying, what is the probability that x equals 1 for a binomial? And given our sample size and the rest, the probability success. So we would have the probability that x equals 1 would be 6. That's the sample size. And then here, our k would be 1. So 6 choose 1. And then the probability of success, p, 0.45, raised to the power of k, which in this example is 1, times the probability of failure raised to the power of the sample size 6 minus k, which is 1. So when you simplify, you get 0.1359, which is the probability that exactly one of the baby boomers is still in the workforce. What is the probability that at least 5 of the baby boomers are in the workforce? So again, here's our distribution for a binomial, and this is below it is the information that we have as far as sample size and the probability of success. So what is the probability that at least 5 of the baby boomers are still in the workforce? So the probability of at least 5 would be x greater than or equal to 5, which is equivalent to finding the probability that x equals 5 and the probability that x equals 6. And the reason why we're stopping at 6 is because our sample size is 6. So that's equivalent to 6 choose 5 times the probability of success to the 5th, which is k, right? And then 0.55 raised to 6 minus k, which is 5. So then plus the probability that x equals 6. So that's going to be 6 choose 6 times the probability of success to the 6 times the probability of failure to the first power. And so you get 0.069 as the probability that at least 5 of the baby boomers are still in the workforce. What is the probability that fewer than 2 of the baby boomers are still in the workforce? So fewer than 2 would mean strictly less than 2. And so that's going to be the same as the probability that x equals 0 plus the probability that x equals 1. So the probability that x equals 0, we're going to use this equation, but we're going to have now k equals 0. So if you plug in 0 for k's, you get this. And then the probability that x equals 1 here, k equals 1. So if you plug in 1 for the k's, you get this. And we also solved this for part A, the probability that x equals 1, which was 0.1359. So that's this. And then we're adding it to the probability that x equals 0. So when you add those together, you get 0.1636. What is the probability that more than the expected number of the baby boomers are still in the workforce? Okay, well, there's two steps to this problem. First, we have to find what that expected number is, and then we need to see what the probability that more than that expected number of baby boomers are in the workforce. So to find the expected value for a binomial distribution, that's going to be n, the sample size, times p, the probability of success. So that would be 6 times 0.45 for this example, which is 0.27. So that is the expected number of baby boomers that are still in the workforce. But now we want to find the probability that more than the expected number of baby boomers are in the workforce. So we're going to do the probability that X is greater than that expected value of 2.7. And so that's going to be equivalent to the probability that X equals 3 plus the probability that X equals 4 plus the probability that X equals 5 plus the probability that X equals 6. And we're stopping at 6 because that's our sample size. And so we already calculated the probability that X equals 5 and the probability that X equals 6 right here. And so all that's left to calculate is the probability that X equals 3, the probability that X equals 4, and then we're going to add everything together. So you can use this equation here and plug in K for 3, or 3 for K, and then 4 for K. So that's how I get these two, and then adding everything together, which essentially you'll be also plugging in 5 for K and 6 for K, but like I said, we had already done that here. So once you add these numbers together, you get 0.5585. So that's the probability that more than the expected number of the baby boomers are still in the workforce. Let the mean success rate for a Poisson process be 8 successes per hour. So here on this upper left-hand corner is the distribution for a Poisson. And so we want to find the expected number of successes in a half-hour period. So if we know that there's 8 successes per hour, which is lambda, our lambda for this situation is going to be, well, we're interested in the number of successes per half hour, so we're going to divide 8 by 2 to get 4 successes in a half-hour period. So lambda would equal 4. Find the probability that at least 2 successes in a given at least 2 successes in a given half-hour period. So since we're dealing with a half-hour period, our lambda is going to be 4, which we just discussed for part A. But now we want to find the probability of at least 2 successes. So that would be the probability of 2 or more, so greater than or equal to 2. And what's easier to compute is 1 minus the probability, the complement of this. So that would be 1 minus the probability that X is less than 2, which equals 1 minus the probability that X equals 0 plus the probability that X equals 1. And so the probability that X equals 0 for this situation, for this Poisson process, we have 4, which is our lambda, raised to the 0, which is our K, divided by K factorial, so 0 factorial times e to the negative lambda, or e to the negative 4, which 4 to the 0, anything to the 0 is 1, and 0 factorial is also 1, so this is 1 over 1, so we're left with e to the negative 4. Now what about the probability that X equals 1? So that's going to be 4, because we have lambda to the K, so that's 4 to the 1, divided by K factorial, so that's 1 factorial, times e to the negative lambda, which lambda is 4, so e to the negative 4. So 4 to the first power is 4, divided by 1 factorial is 1, so that's 4 times e to the negative 4. And so when you simplify, you get 0.908422, Find the expected number of successes in a 2-hour period. So previously, we were given that we have 8 successes per hour. So for a 2-hour period, we now want to multiply by 2. So we get 8 times 2 is 16. And now we want to find the probability of 10 successes in a given 2-hour period. So now our lambda is going to be 16, as we discussed in part C. And we want to find the probability that x equals 10. So here we have lambda to the k, so that would be 16 to the 10 divided by k factorial, or 10 factorial, times e to the negative lambda, so that would be e to the negative 16. So when you simplify, you get 0.034098. Motorists arrive at a Gulf gas station at the rate of 2 per minute during morning hours. So here, we're still dealing with the Poisson process. What is the probability that more than 2 motorists will arrive at the Gulf gas station during a 1-minute interval in the morning? So the average number of motorists arriving in 1 minute is lambda equal to 2. That's given to us. And so we're still dealing with a 1-minute interval. So lambda isn't going to change, because here we're given per minute, and so 1-minute interval, our lambda is going to be 2. But we want to find the probability that more than 2 motorists will arrive at the gas station. So that would be x strictly greater than 2, which is equivalent to 1 minus the probability that x is less than or equal to 2. This is easier to solve, right? 1 minus this complement. So that's going to be 1 minus the probability that x equals 0 plus the probability x equals 1 plus the probability that x equals 2. And so the probability that x equals 0 for this situation, where we have lambda equal to 2, is going to be lambda to the k, so that's 2 to the 0 divided by k factorial, so that's 0 factorial, times e to the negative lambda, so that's e to the negative 2. So 2 to the 0 is 1 divided by 0 factorial, that's also 1. So we have 1 over 1, which is e to the negative 2. That's this number. And then for the probability that x equals 1, that's going to be 2 to the k. So that's 2 to the 1 divided by 1 factorial times e to the negative lambda, e to the negative 2. And so this is equivalent to 2 over 1 times e to the negative 2. So we get 0.2707. And then lastly, we also need to find the probability that x equals 2. So that's going to be 2 to the 2 divided by 2 factorial times e to the negative lambda, or e to the negative 2. So this becomes 4 over 2 times e to the negative 2, which is 0.2707. So when you do 1 minus this quantity, you get 0.3233. What is the probability that exactly 6 motorists will arrive at the Gulf gas station during a 5-minute interval in the morning? So note, now we're dealing with a different interval. So previously we were dealing with a 1-minute interval, but now we're dealing with a 5-minute interval. When we were dealing with a 1-minute interval, lambda equals 2. So now we want to do 2 times 5, because we have 5 minutes, so that's 10. And then we want to find the probability that exactly 6 motorists arrive. So that would be the probability that x equals 6. So here, and again, we have lambda equal to 10. So we would have lambda 10 to the k, which is to the 6, divided by k factorial, that's 6 factorial, times e to the negative lambda, or e to the negative 10. So when you simplify, you get 0.0631. How many motorists can an employee expect in a 3-hour morning shift. So now we're needing to know the expectation, but also we have a 3-hour morning shift. So previously we were dealing with lambda for 1 minute, but now we want to find how many minutes are in a 3-hour morning shift to adjust our lambda. So in 3 hours, we're gonna have, well, for each hour, there's 60 minutes. So if we do 3 times 60, you get 180 minutes. So, and for a Poisson distribution, the expectation is equivalent to lambda. So our lambda is going to be 2, because that was how much the average number of motors per minute times, and here we have 180 minutes, which we found above. So 2 times 180 is 360. So that's the number of motorists that an employee can expect in a 3-hour morning shift. A committee of 10 is to be chosen from 50 people, 25 whom are Republicans and 25 who are Democrats. The committee is chosen at random. What is the probability that there will be 5 Republicans and 5 Democrats? So I've used R to denote Republicans and D to denote Democrats. So the probability that 5 Republicans and 5 Democrats are chosen for this committee would be, so here we have 25 Republicans and 25 Democrats and a total of 50 people. So the denominator is going to be 50, the total number of people, choose 10, because the committee is going to be made up of 10 people. So that's going to be the denominator, taking all of the possibilities, all the people, so that's 50 divided, and then 50 choose 10 of the people. But the numerator is going to be, so here we have 25 Republicans, and we're going to choose 5 of those, and then 25 Democrats, and we're going to choose 5 of those. So we get 25 choose 5 times 25 choose 5 divided by the total possibilities, which is 50 choose 10, which equals 0.274798. What is the probability that a majority of the committee will be Republicans? So the majority of Republicans, so let's recall that we have a total of 10, is the committee is going to be made up of 10 people. So if we have a majority of Republicans, that means that we're going to have either 6 Republicans, 7, 8, 9, or 10 Republicans. So we need to add up these possibilities in the numerator and then divide it by the total number of people choose 10. So the numerator is essentially, so we're going to start at 6, right? Because that would mean if we do 25 choose 6, then we know that the committee is only made up of 10 people. So then for Democrats, that's going to be 25 choose 4. But then we need to add up, there's, more possibilities, right? Because we could also have 7 Republicans and 3 Democrats, or 8 Republicans and 2 Democrats, 9 Republicans and 1 Democrat, or 10 Republicans and no Democrats. So the numerator is made up of this sum, and then you divide that by 50 choose 10 to get 0.3626. So that is the probability that the majority of the committee will be Republicans. A professor of management has heard that 8 students in his class of 40 have landed an internship for the summer. Suppose he runs into 3 of his students in the corridor. Find the probability that none of these students has landed an internship. So again, he has a class of 40, and he's heard that 8 students had an internship. So if we do 40 minus 8, then we have 32 students. So to find the probability that none of these students landed an internship, that's going to be, and then he ran into 3 in the hallway, right? So there's 32 students total that we know did not get an internship, and he wants to know if these 3 particular students had an internship. So or 3 students that these did not, none of these students landed an internship. So that's going to be 32 choose 3 divided by his total number of students, choose 3, right? Because there's 3 students that are in the corridor in the hallway. So when you simplify, you get 0.5020. Find the probability that at least one of these students has landed an internship. So the probability that at least one has landed an internship is equivalent to 1 minus the complement of that, which would be that no one has landed an internship, which we had found in part A. So we would just do 1 minus 0.5020 to get 0.498.